So we finished up last time talking about kinematics. We'll come back and visit kinematics when we transition from particles to rigid bodies. But we're going to move on to kinetics. We covered in just under 3 weeks, we covered about 100 years of history. We talked about Galileo's work in kinematics, and now we're moving on to Newton's work in kinetics. If we wanted to put a date on this, Newton published this in about 1687, to give you a date to put on this. And that was then the classic 3 laws: Newton's first law, Newton's second law, and Newton's third law. Remember, his first law says that an object that is at rest or moving in a straight line with constant velocity will remain that way unless acted on by an unbalanced force. The second law comes up with the expression, the sum of the forces is equal to mass times acceleration, and we'll see that a little more very quickly here. And then the third one, sometimes people forget, but you shouldn't. It may be the most important one at all. That is the force of action and reaction between two bodies is equal, opposite, and collinear. Okay, so we'll use all of those in our work. They're repeated in your textbook. They're repeated in your physics book, so I'm not going to write them up here. But if we start to think about this, let's say that we take a particle, and we're going to do this initially for a particle. We'll talk later in the term about how this how a rigid body affects this, but we'll first look with a particle, just like we've done with kinematics. So let's say I apply a force F2 to something, and it's going to move. It's going to accelerate, and it's going to experience an acceleration. We'll call that A2. And if I would have applied a force F1, maybe in the same direction, maybe in a different direction, it's going to then experience an acceleration, A1. So if I look at the ratio of that, if I look at the ratio of F1 to A1 and take its magnitude, and the ratio of F2 to A2 and take its magnitude, I come up with some constant. And that constant is, of course, mass. And mass may go by several different names. Some people might call it inertia. Some people might use a more wordy statement and say it's a resistance to velocity change. But that is all, in a sense, talking about mass. From a practical standpoint, mass has units. It would be kilograms, or it would be a slug in the English system, where the base units on a slug would be equal to pounds times seconds squared divided by feet. Of course, in the metric system with kilograms, that is the base unit because it's a mass system, unlike the English system that is a force system. So mass is really resistance to velocity change, and we'll see that over and over again. If you get into a situation, maybe if you're structural and you've designed a floor system that has a little too much vibration in it, you can actually fix that. One of the easiest ways to fix it is just see if they want a grand piano in there. You just buy them a grand piano, put that in there. What are you doing to the floor system? You're adding mass to it, and that will tend to damp it down. So that's always kind of a joke in the structural community. Would you like a grand piano? So anyway, well, of course, I've written this equation a little differently. This is Newton's second law, that the sum of the forces is equal to mass times acceleration. As we go through this, the notion of a free body diagram is going to be very important, because now we're back talking about forces. You'll notice for a few weeks now we haven't talked about forces, and the direction of those forces and the corresponding accelerations are going to be important. So we'll have to talk about that too. I thought I'd open with an example, though.
An interesting problem that relates to what we're talking about with Newton's second law involves a steam catapult, what they use to launch aircraft off an aircraft carrier. I used to have some interesting pictures that I would show the class, but since I'm going online with this, I have to be more careful of copyright and whatnot, things that you show in the classroom. You can't necessarily post up on your video channel. So if you're wanting better pictures of this, you could Google steam catapult or aircraft launching off of an aircraft carrier or something like that. But suffice to say, I've got a diagram here, and what happens is you've got these two tubes. Usually there's two of them side by side, and they put steam in here. This is the way they've been doing it for quite a while. They originally started with some counterweights, and probably now they may be even looking at using magnets and things like that. But for the longest time, they took and they put steam in here. So you'd have a piston in here, and that piston would be attached to the front wheel of the aircraft, and as you put steam into here, that steam expands about 1,000 to 1, and that would cause that to the piston to zip down there and then pull the aircraft off of the ship, just like a steam engine works and whatnot. If we look at it from this direction here, we'd get that view right there. Usually you have a couple of those steam chambers side by side, and they are hooked together, and the whole ship is going to be running on steam, the propulsion system, so they can just divert one of the reactors or one of the boilers or however they're making the steam with of course reactors nowadays, and use that to very effectively launch aircraft. And I've got some statistics here. The one that I'm looking at is off the USS Enterprise, and it's 249 feet long, so that's kind of interesting in and of itself. It's a really long one, and it'll launch a 35-ton F-14, so it's a little bit older here, but 35-ton F-14. It'll launch it from 0 to 150 miles per hour in 4 seconds. So with this data, let's see if we can do a little calculation, and we'll talk about how good our calculation is based on this very rudimentary set of data. Maybe we would need some better values to get a little more complete and maybe a better answer. But it'll give us something to start on. So let's go ahead and do that.
Okay, so if you remember those numbers, and this is just a magazine clipping, so we don't have a lot of information, so I'm going to have to assume constant acceleration, and that is probably not a very good assumption. The acceleration is probably going to be higher initially and lower as it gets out towards the end, thinking about how steam works and whatnot, but lacking other information, the best I can do is assume a constant acceleration. So with constant acceleration, I'm going to go back to my kinematics equation that the velocity is equal to the initial velocity plus the acceleration times time. And if I take that 150 miles and I convert that, that would be multiplying by what, 5,280 and dividing by 3,600. We've done that before. We'd get 220 feet per second. So using feet per second, I put that in for my velocity. My initial velocity, it starts from rest. So that's from 0 to 150 miles an hour, or 220 feet per second in 4 seconds. And we can calculate the acceleration, which is 55 feet per second squared, which turns out to be about 1.7 Gs. And I think most people say that those pilots initially experience about 3 to 4 Gs. I guess no one was on an aircraft carrier, so you mean no one flew aircraft off an aircraft carrier, right? Okay. So no one's had a steam catapult in their backyard, so we've just got to trust what people say. But most people say they experience 3 to 4 Gs. So our number is a little lower than that, which would indicate that our assumption is probably not very good for constant acceleration. I think most people would agree that the acceleration is probably higher initially and lower towards the end of the catapult. But anyway, with the data we have, we'll take constant acceleration and we will look at this acceleration 1.7 Gs. So now we take the aircraft that's 35 tons, which turns out to be 70,000 pounds, which is worth thinking about. I mean, the classic 18-wheeler truck, the Class 8 truck, whatever you want to call it, going down the highway, it is usually limited to what? With 18 wheels in the classic arrangement, they're limited to how much weight? Usually says right on the door, 80,000 pounds. Okay, so sometimes they put more axles in them and whatnot, and then sometimes they'll go up to 105,000 pounds, but the classic 18-wheeler is going to be at 80,000 pounds. Okay, so this is basically slinging an 18-wheeler off the deck when it's loaded. So what I'd like to do is, using Newton's second law, force is equal to mass times acceleration, I'd like to come up with a force that it takes to make this happen. So I could say that this would be equal to the mass, which is going to be 70,000 pounds divided by 32.2 feet per second squared. So that's the mass term, because 70,000 pounds, that's a force term. I divide by the acceleration of gravity, and I now have a mass term. And then did we have an acceleration? We certainly did. That was the 55 feet per second squared. So when you go through this, when you run the numbers on this, you get 119,565 pounds, which we could say was about 120 kips. About 120,000 pounds. Okay. And I'm not a real aircraft buff. I don't know a lot about aircraft in terms of, F this from the, F-14, F-15, F-16. They didn't even have a 17, did they? Maybe someday we'll pay for a 17. But anyway, I can always tell whether it's an Air Force aircraft or a Navy aircraft because what's one telltale sign of a Navy aircraft besides the insignia? The landing gear is much sturdier, right? Okay, they really don't land on an aircraft carrier. It's called a controlled crash. So the landing gear has to be much sturdier than an Air Force rig that they'll just bring down real carefully on a runway. The other thing that has to be a lot sturdier is this catapult is hooked to where on the aircraft? Hooked to the front wheel. Okay, so you've got a lot of force trying to tear that front wheel off. And granted, you might say, well, not all of this is transferred into the front wheel because the engines on the aircraft apply a lot of thrust, and that's true. But also, we probably have we used a lower acceleration value. So we would expect the force initially on that front wheel to be really quite high. So some kind of interesting numbers to play with. Probably not real numbers because we don't have our exact acceleration, but gives us some ballpark numbers to think about. And also a good use of Newton's second law, force is equal to mass times acceleration, and being careful with the units. I had to be very careful with my force there. Questions on that? So 120,000 pounds, that's a lot of force. You'd have to really design that front wheel assembly pretty well. Well, before we venture into this too much, we probably should talk about degrees of freedom, which really means the number of equations that we need to solve the problem. So if I talk about a situation, for instance, where I have this wire, let's say I take a little wire and I put a bead on that wire, that bead is constrained to the path of that wire. And we could say that the position of that wire is given along there. We've got that position S. And if I talk about an x value and a y value, I could say that y is really some function of x. Well, what's that function? The function is the shape of the wire, isn't it? Okay? That's like a train on the track. If you know x, do you know y? Yeah, if you know the shape of the track. Okay? This is sadly the manifesto of the crazy person up at Clackamas Town Center that started shooting at people. We didn't really hear a lot about that in the news because a few days later the very tragic event at Sandy Hook happened. But in his manifesto, he said he wanted to have freedom and be like a train on a track, which is pretty moronic, isn't it? Yeah, I mean, why wouldn't you pick an airplane or a submarine? You'd have more degrees of freedom, wouldn't you? So the little train that could. In that case, I think it was a little train that was a moron. But anyway, I always think about that. You put a train on a track, you have 1 degree of freedom. A bead on a wire, that's 1 degree of freedom. So I really only need one equation to solve that. As we get into more degrees of freedom, let's say that we've got a point, and it's in a two-dimensional plane. So we can describe this with either x and y, or we can describe this with r and theta. We have 2 degrees of freedom. Okay? We have 2 degrees of freedom. We're going to need 2 equations. Maybe that would be some of the forces in the x is equal to mass times acceleration in the x. Some of the forces in the y is equal to mass times acceleration in the y, right? If you haven't already noticed, when we studied all last term with statics, it was just a special case of this where these accelerations were equal to 0, right? I mean, if we were to study from the general to the specific, we really should study dynamics first, and then go back and look at the special case being static. Okay, that would be a little bit like saying that you should really learn to run first because crawling is just a special case of running. Okay, that's probably true, but it doesn't make good practical sense. Okay, so remember in statics, the right-hand side of these equations was just equal to 0. Now we're looking at non-zero terms on the right-hand side, which is going to make a good free body diagram even more valuable this term. Well, if I look at a particle in space, so I go into, I look at a particle in space, I could have, depending on my coordinate system, I could have x, y, and z, r, theta, and phi, cylindrical coordinates, what, r, theta, and z, all different possibilities, but I have, at the end of the day, 3 degrees of freedom, don't I? I would have 3 equations. I could tolerate 3 unknowns. And maybe let me skip to a body in space. So I take this, instead of just a point, I have this body in space, like maybe an aircraft. So I would have the 3 degrees of freedom from the particle in space, because I could talk about the center of that aircraft, right? Its latitude, its longitude, its elevation, X, Y, and Z, if you will. But then that still doesn't describe the orientation of the aircraft, does it? Do we have any pilots here? Anyone plays a pilot on TV? There we go. He plays a pilot on TV. Thank you. So, video game? Grand Theft Auto? Okay. Okay. I left myself open for that one. Okay. So, you not only have latitude, longitude, and elevation, but you also have pitch, yaw, and roll, right? Pitch, yaw, and roll. So that would give you 6 degrees of freedom. Your latitude, your longitude, and your elevation, that would place your center, and then how you're oriented, whether you have a pitch, roll, and yaw. So 6 degrees of freedom there. Well, for our initial study here, we're just going to look at particles. Our most complicated problem would be 3 degrees of freedom, but later in the term we'll come back and we'll look at this for a rigid body, and we'll have then those 6 degrees of freedom. The end of the story on this is if you have a problem with 2 degrees of freedom, you're going to be limited to 2 equations, right? So some things to think about there. Well, I've been talking about the importance of free body diagrams. We took a few weeks off of that, but they are very important when we come back and we start looking at kinetics. So let's say that we have a little problem like this. We've got a very simple problem of a crate sitting on a flat surface. We'll say that we have negligible friction there, and we're applying a force to it. We don't apply the force horizontally. We apply it from an upward angle. Yes?
Would another way of saying that be that the degrees of freedom is equal to the number of variables?
Well, degrees of freedom would be the number of variables and the number of equations we're going to use. Yeah. So I've got this 50-pound crate, and I'm applying this force to it, and it's not horizontal and it's not vertical. It's at some angle, and I'd like to find the acceleration. And sometimes people, they'll not only draw a free body diagram, but they'll draw what's known as a kinetic diagram. Let me go ahead and draw a free body diagram here. So if I draw the free body diagram, I'm going to have, of course, 50 pounds acting down. And then I would have, by Newton's third law, I would have the normal force acting up. And then I'm going to have the horizontal force there, right? So I'd say that this was 200 times the cosine of 60. And then I'd have this piece over here that would be 200 times the sine of 60. And we said negligible friction, so the friction force, that's going to be 0. Have I accounted for everything? I've got the normal force, I've got the weight, I've got the applied force. I think we're good. But the one thing that I haven't put on there is the acceleration. So sometimes they'll talk about a kinetic diagram. Sometimes they go over here and they draw this kinetic diagram and they show the acceleration on that. I don't like to have 2 diagrams. I like to have everything on 1 diagram. So oftentimes what I will do is, separate from this a little bit, I'll draw a double arrow and I'll say that's my acceleration. Okay, so I don't want to confuse my acceleration, which is not a force on that diagram, but I like to have it there. Now you'll notice that I just put that acceleration going to the right. If I'm wrong on that, I'll just get a negative number. That's not a problem, so I'm not going to spend a lot of time trying to figure out which direction it goes. Well, how many equations am I going to need on this? Maybe I'll ask a different question. How many unknowns do I have on this? Yeah, I have 2 unknowns. I have the normal force and I have the acceleration, don't I? Okay. If I was trying to solve and I had friction in here, I'd definitely have to look at the equation in the vertical to get that. As this turns out, I could really get this acceleration here if that's all I'm looking for with 1 equation in the horizontal direction. But if I wanted to find the normal force, I'd have to have a second equation. Well, let me go through those equations. I could say that the sum of the forces in the vertical direction is equal to mass times acceleration in the vertical direction. And what's the acceleration in the vertical direction in this problem? Yeah, I'm hoping it's 0. I'm hoping it's not bouncing up and down as it's going along. I want that to be equal to 0. So we come back to an equation like we might have had last term in statics, that the sum of the forces in the vertical is equal to 0. And I could talk about the normal force. I'll go ahead and take positive up here. The normal force minus 50. Anything else? Minus 200 times the sine of 60. So I could, with that equation, come up with a normal force. Now, that would be very important if I had the friction force, because you know that the friction force is equal to the coefficient of friction times that normal force. I'm not necessarily interested in that, so maybe I'll move over here and look at the sum of the forces in the horizontal direction, setting it equal to mass times the acceleration in the horizontal direction. And what do I have? I've got the sum of the forces in the horizontal is equal to the mass on this thing. What's that going to be? 50 divided by 32.2, because 50 is a weight, it's not a mass. And I'm going to be multiplying that by A. That is the acceleration in the horizontal direction, isn't it? So plugging in my horizontal forces, what do I have? I'll take positive to the right. I've got 200 times the cosine of 60 minus 0. I don't have anything opposing that, is equal to 50 divided by 32.2 times the acceleration. So I could solve for the acceleration there. That turns out to be equal to, let's see. So I don't have enough. I have to grab a calculator on that. $64.4. So 64.4, this will be feet per second squared. So that would be the acceleration. But you expect it to have a pretty high acceleration if you're applying a, 200 cosine 60, that's just 100 pounds. You take something that's sitting on ice with a little water between it and apply 100 pounds to it in the horizontal direction, you're going to expect that thing to get moving right along. A pretty large acceleration, right? Okay. But this is probably not the important part of this problem. Right answers are important, but properly doing a free body diagram, that's key as we go forward. Questions with that? I've said the sign convention here. We'll have to be very careful with this. It seemed obvious that we take the acceleration as positive, but our sign convention that we have on the left-hand side of this equation is going to be the same sign convention we have on the right-hand side of the equation. So if our acceleration was pointing back this way, we would have had a negative acceleration there. So the sign convention that we use on the left side of the equation has to be the same as the right-hand side of the equation. Well, I don't have numbers on this one, but let's draw a proper free body diagram for it. That's going to be the key part there. We've got some sort of a crate or package on an inclined surface. If I draw the free body diagram for that, what's that going to look like? Well, I'm going to have what? The normal force. That's the ramp pushing back on this thing. So I have the normal force. We were told we have a coefficient of friction, so presumably it's moving up the slope. So I'm going to put the friction force. That's going to be mu times n opposing that motion. I could put this force that's applied there. It looks like to be applied in the horizontal direction. And I have then the weight on this thing acting like that, right? And if I looked at some angles in here, this would actually be the angle alpha. And as far as this goes, that would be the angle alpha, wouldn't it? Okay. So that's a proper free body diagram. I think then what direction should we look at? I mean, you could, if you wanted to, take x and y and look at it in a horizontal and vertical direction. Or if you wanted to, There'd be nothing wrong with rotating the coordinate system, saying that x is up the ramp and y is perpendicular to the ramp. Okay, it's a judgment call probably on this one because you got two that are parallel and perpendicular to the ramp. You got two that are parallel and perpendicular to vertical and horizontal. So in this case, it's going to be a judgment call. If this force were in this direction, then I would say probably this would be the way to go. Now, if you use a coordinate system like this, you're going to be finding probably the acceleration parallel to the ramp and perpendicular to the ramp, right? So you have to think about what directions your acceleration is going to go. And if this force is sufficient, which way do you think the acceleration would be? Like that, right? Okay. And if you're not convinced of that, if you think it might be down, that's fine. We'll let the math take care of the sign on that. Yes?
Are we going to do some stuff where we figure out like at what angle, given some force, would the box not go up but actually tip over?
Yeah, I think the question is trying to figure out this angle for motion or up and down the plane. Is that right? I think you've got some homework problems, and we're going to address them also in class where you have a car like on a incline, an off-ramp or something, maybe on a freeway system, and we look at that car. I know, an odd-looking car. But we look at if it's going around there, if it's going too fast, it's probably going to accelerate up. If it's going too slow, it may start to accelerate down. So, yeah, we will definitely spend some time talking about things like that. Other questions? Let's try a problem that should be fairly simple, but if we try and make it too simple, our intuition can get us into trouble here. Let's say we take a fairly simple system of a couple pulleys. We throw a rope or a cable over those pulleys, and we attach to one side, we attach a 100-pound weight. To the other side, we attach a 50-pound weight. Remember, a Freebody diagram is always a diagram of forces, not masses. But then when we start working with Newton's second law, oftentimes we need the masses. Here we've got the values in pounds, so we know that they are forces. We'll have to be careful with that. And what we'd like to do is we'd like to find the acceleration of that 100-pound weight. I think most people realize if we set this up and we're holding it here and all of a sudden we let go, what's going to happen? The 150 is probably going to go down and the 100 is probably going to go up, right? So let me go ahead and assume that I have some acceleration here, and that's what I'd like to find. Now you might say, well, if you're not comfortable assuming that that's going up, that's okay. Go ahead and assume it going up. If we get a negative sign, you are right. It really wasn't going up. Okay? Not a big deal. So a couple assumptions that I'm going to have to make. I'm going to have to say that the length is equal to a constant, and that the mass is approximately equal to 0 for the pulleys and for the cable. If we had very massive pulleys or we had very massive cable, we might have to account for that. But we've got a system with, 250 pounds here. If our cable and our pulleys are a couple pounds, that's probably pretty minute, right? We're also going to assume that that cable does not stretch. It's not a rubber band. It's not a bungee cord. Does rope or cable stretch? Yeah, but if we're talking about a stretch of a 1/4 inch, that's probably not going to be a big deal in this system. Okay, so what I'd like to do then is I'd like to look at a free body diagram. Maybe I'll do a free body diagram of the 100-pound weight. And what do I have there? I got 100 pounds acting down. And I'm going to have some tension in that rope pulling up on that. And I think we already agreed that there is some acceleration. So let me put that acceleration there. Okay. And the mass on this thing, let's be clear with this, the mass is going to be equal to 100 divided by the acceleration of gravity, g, 32.2 in this case. We're assuming it's on Earth. So if I were to solve this problem, if I were to come over here and say that the sum of the forces in the vertical direction is equal to mass times acceleration in the vertical direction, how many unknowns do I have? Two unknowns. I don't know this tension force, and I don't know the acceleration. So what's a good plan for me? Should I guess one of them? Call the psychic hotline, see what they have to say? Probably not a rational approach, is it? What would be a rational approach that an engineer would take? Yeah, free body diagram of the other side. Have the discipline to go make another free body diagram and come up with another equation. So here I have, what, 150 pounds. I'm going to have some tension T here. I think most people recognize if you have tension T there, you're going to have the same tension there, right? We've probably got through that in statics. And the other thing is, and some of you may not be prepared to commit to this as accelerating up, but if we assume that this is accelerating up, which way do we have to assume that this is accelerating? Yeah, so we're going to take the acceleration A here. Now we don't have any moving pulleys, we don't have a fancy pulley system, so whatever acceleration up we have here, we get the same value down over here. And the mass in this one is going to be equal to 150 divided by g. So if I go through this one, if I look at this one and say that the sum of the forces in the vertical direction here is equal to mass times the acceleration in the vertical direction, I again come up with too many unknowns, t and the acceleration a, right? But if I go through this, let me go ahead and take positive up here. I could say that I have t minus 100 is equal to the mass, which is 100 over g, times the acceleration a, because a is up and positive. So there's one equation. And I could, this one, say that I have, and I'll go ahead and take up as positive here, I have t minus 150 is equal to 150 divided by g times the acceleration in the vertical direction. What do we have? A is acting down, so I'm going to have minus a, aren't I, according to my sign convention. I'm kind of messed that up. That's pretty important. Let me fix this up here. So we've got minus a. Okay, minus a. So I have two equations with the same two unknowns. I can solve this problem, can't I? If I say that this is equation 1 and this is equation 2, I can solve equation 1 and 2 for the tension T and the acceleration A. We weren't interested in the tension, but that comes from that solution. And we would get, as we go through that, two equations, two unknowns. You can hand that to your little brother or sister that's in middle school algebra. You had 120 pounds here, and the acceleration would be equal to 6.44 feet per second squared. You might say, well, I got a g in there. Well, that's just 32.2, right? So that's not a big deal. You comfortable with us solving those simultaneously? You could do a substitution, you could do simultaneous. If you really wanted to make a big deal, I'll grab a computer algebra system. Does this make sense? Do these answers make sense? I mean, while we wanted the acceleration, I think the tension is probably the easiest one to ask, does that seem reasonable? If it was static, what would we expect the tension to be there? Well, let's see. Is it 100 or is it 150? I don't know. Somewhere between 100 and 150, wouldn't we? We'd expect it to be somewhere between there. Okay. Which brings us to some people saying, well, I could shortcut this whole process. And I'm going to try it a little different way. Could I make this easier for myself? I don't like two equations and two unknowns. Why don't I just say that I have something like this? Maybe I'll take this 100 pounds here. This is what we're looking for the acceleration of. And I could just come over here and I have this pulley system. And why don't I just put 150 pounds here? Think that'd be a good model for me to work on this? Well, it's always good to try and find shortcuts, but you got to find a shortcut that'll get you there and not leave you stranded in the middle of somewhere. Let's see if this one will get us there. So we come up, when we look at a Freebody diagram on this thing, we're going to have 100 pounds acting down. I'm going to then take, if I have 150 pounds here, we would have 150 pounds here. I'd have some acceleration. That's what we're looking for. That's good. And this has a mass that's equal to what? 100 divided by g, which is 32.2. So if I sum my forces in the vertical direction set equal to mass times acceleration in the vertical direction, I'll go ahead and take positive up. We have 150. I'm liking this. I don't have that stupid t hanging around, right? Minus 100 is equal to the mass, 100 divided by 32.2 times acceleration in the vertical direction. One nice equation. I get the acceleration in the vertical direction is equal to 16.1 feet per second squared. And of course t, that was 150 pounds, wasn't it? Are they the same? No, they aren't. We should have recognized right off when I proposed this that this was not good, because in the previous problem we had that t was 120 pounds. Here we're trying to say that t is equal to 150 pounds. That's going to give us a different acceleration, isn't it? So why didn't this work? Well, it didn't work because if I come over here and I look at this system, this is not pulling on it with 150 pounds, is it? Because it has to be, we have to account for its own acceleration, right? If it was the static situation, we'd have 150 pounds here, but we don't have the static acceleration, or we don't have the static situation. We have this thing accelerating down. And if this happened to be accelerating down at 32.2 feet per second squared, what would be the tension in that? Actually be zero. It'd be in free fall, wouldn't it? Okay. So while this shortcut was a nice try, we tried to get a little easier equation. It didn't work, did it? So as we change models to try and make them easier, that's important. We want to try and make the model as simple as possible. A lot of people go around, well, it's very complicated. I couldn't explain it to you, they say. Okay, well, that means you can't explain it. Okay, so you want to make the model good enough to cover the situation, but you don't want to make it too simple. We made this too simple. So this 150 pounds is very different than having a 150-pound weight hanging there that's accelerating. It basically boils down to the difference between that 150 and this 20 that we have here. I mean, had we gone through this problem and we knew that this was 120, we could have actually shortcutted this thing and said, well, instead of 150, I have 120 there. Would we have got the right answer? Yeah, we would have got the right answer with that, but how did you know it was 120? Okay, so make the problems as simple as possible, but not more so. This is the solution you want to look at. Okay. Well, we're going to continue on in this. I've got another problem here. I'll just give you a sneak peek. The classic elevator problem. Got a 75-kilogram person stands on a spring scale in an elevator. During the first 3 seconds of motion from rest, the tension T in the lifting cable, the hoisting cable of the elevator is 8,300 newtons. We'd like to find the scale reading if the system mass is 750 kilograms. Okay, so this is going to be a good problem for concepts of system, for concepts of accelerating up and down. This goes to the classic example. When you go into an elevator and you stand on a scale and you press the up button and you accelerate up in the elevator, the spring scale is going to read what? It's going to read heavy, isn't it? Okay? And if you're in, trying to meet your Weight Watchers challenge, you would really want to get in the elevator on a high floor and stand on the spring scale and push the down button, because the spring scale is going to read what? It's going to read light. Okay? Now, if you didn't want to have this problem of reading light and reading heavy, you'd have to use a balance, wouldn't you? Because if you use a balance, the weights that you use on that balance would be affected the same, wouldn't they? Okay. So that's probably why in your physics and your chemistry classes you don't weigh things, you mass them, don't you? You mass them with a balance. So So this will be the problem that we start with next time. I'll put it up again if you didn't get to it, and we'll go from there. Very quickly, we'll also start to look at things instead of moving in a straight line around corners, so that'll be a lot of fun as we look at curvilinear motion with this. So that's where we'll go next time. Take care till then.